All right, this is going to be our walkthrough for the homework assignment titled More Integral Motion. We're starting off with a velocity of a particle moving along the x-axis given by v of t is 3t squared minus 3 for t greater than or equal to 0. And we're given that the particle is at x equals 16, a position of 16, when t is 3. We want to find the position at t equals 1. Well, this should be pretty straightforward. To get a position function, we just need to integrate our velocity function. We'll call it x of t. That'll be the integral of v of t dt. And we can then just integrate 3t squared minus 3, which comes out to be t cubed, right, if you integrate 3t squared, and minus 3t if you integrate the minus 3. Of course, we have to attach a constant to that, right, because anytime we integrate, we have to attach the constant to it. And we know that x of 3 is equal to 16. So when I plug in 3 to this, 3 cubed minus 3 times 3 plus c, I need to get 16. In other words, 16 is equal to 27 minus 9 plus c. Or 16 is equal to 18 plus c. Right? 27 minus 19, that's just 18. So if I subtract the 18 over, I get c is negative 2. Which tells me that my position function, x of t, is t cubed minus 3t minus 2. And in order to find the position at 1, we just need to plug in 1. 1 cubed minus 3 times 1 minus 2. 1 cubed is 1. 3 times 1 is 3. We have 1 minus 3 minus 2, which is a position of negative 4. Now, the second part of this is asking us, when is the particle moving to the left and when is the particle moving to the right? Well, particles move to the left when their velocity are negative, and they move to the right when the velocities are positive. So we just need to see when is v of t greater than 0 and when is it less than 0. So what we'll do is we'll just set v of t, which was 3t squared minus 3 equal to 0, because that tells us when it might change from positive to negative. It can only change from positive to negative when it's equal to 0, and because this function is a continuous function and has never has places where it's undefined. So we would just end up solving this. You can either factor it or you can just add the 3 over and divide and square root. But regardless of which way you do it, you'll end up with the same answer. And 3t squared equals 3. Divide by 3, t squared is 1. Square root, and you get t is positive 1 or t is negative 1. We'll note that t equals negative 1 isn't in our domain, so we're just going to completely ignore that. And we just have a place where it could change signs at t equals 1. So if we just make a little sign chart for our velocity starting at 0 with one critical value of 1 for our velocity function, right? Then when we plug in something more than 1, like a million, into our velocity function, we clearly get something that's positive. So we're going to get a positive there. But when we plug in something that is to the left of 1 but bigger than 0, like a half, and if we square a half, that's a fourth. And 3/4 minus 3 is negative. So that tells us that our particle is moving left from t equals 0 to t equals 1, and it's moving to the right when its velocity is positive from t equals 1 to, we'll just say, infinity. Right? You could write them in intervals, right? 0 to 1 and 1 to infinity. That'd be fine as well. Right? And our reasoning here is moving left, v of t less than 0. Moving right, v of t greater than 0. All right, our next page here, we still got the same problem, same idea, but we want to know the acceleration of the particle the first time that the particle is at rest. Well, we already determined when the particle was at rest, right? we already set v of t equal to 0 and got that that happened when t was 1. So our particle is at rest at t equals 1. If we want the acceleration when the particle is at rest, we need the acceleration function. Well, that's just v prime of t. Well, that'll just be 6t. So in order to get the acceleration at 1, we just need to do 6 times 1, or 6. So the acceleration of our particle the first time it's at rest is just 6. Our next question is the particle ever at x equals 0? So, and if so, what's the velocity and the acceleration at that time, or those times if there were more than one? So to determine if it's ever equal to 0, we just need to set our position function, which we found in the first part, equal to 0, right? Because that would be when its position is 0. It's at x equals 0. So our position function was t cubed minus 3t minus 2. And we're going to set that equal to 0. Now, this is a cubic function, and it doesn't look like one that we can factor by grouping. So we're going to have to just use synthetic division to figure out how to factor this. The options, of course, come from the factors of the constant, positive or negative 1 and positive or negative 2, all divided by the factors of our leading coefficient of 1, so positive or negative 1. So our options of how this might factor nicely are 1 over 1 or negative 1 over 1, so either positive or negative 1, or the 2 over the 1, so positive or negative 2. Now, I think we probably see that if we plug 1 into this, we definitely do not get 0. So I'm going to start off by testing out 2. I'm going to use synthetic division to test it. I'm going to put 2 in the box. I'm going to put a 1 here for my t cubed, a 0 because there are 0 t squareds, a negative 3 here, and then a negative 2. And I'm going to do the synthetic division. Drop the 1 down first. And anytime you have something that is below the line, then multiply by what's in the box. 2 things above, add them, multiply by what's in the box, add, multiply, and add. Since we came out to be 0 here, we know that this does factor. It factors into t minus 2 and 1t squared from this, plus 2t from the 2, and then plus 1. And I could factor that further. That t squared plus 2t plus 1 is just t plus 1 squared. But we know that t plus 1 squared just would yield t equals negative 1. T equals negative 1 is not in our domain, so we don't have to worry about that, right? This gives t equals negative 1, which we're going to ignore because it's not in the domain. And this one gives us t equals 2. So we want to find the velocity and the acceleration at 2. So the velocity at 2, well, our velocity function was just 3t squared, so 3 times 2 squared minus 3. That's 12 minus 3, or 9, so our velocity is 9. And we want the acceleration at 2. Well, our acceleration function was just 6t, so that would be 6 times 2, which will just be 12. And our last question here with this same idea, the same given function, is the particle's speed increasing or decreasing at t equals 2? Well, it depends on the velocity and the acceleration. But we just found that v of 2 was equal to 9, and that a of 2 was equal to 12. And we know that if the velocity and the acceleration have the same sign, then the speed is increasing. So we will say speed is increasing, and we'll give the reason that we'll say because v of 2 and a of 2 have the same sign. You can indicate if you want they're both positive. You don't have to indicate they're both positive, just so long as somewhere we've shown that they do have the same sign. Right? So our speed must be increasing. And so that's the end of question number 1. That's all of the parts of question 1. So our next one here gives us a particle moving along the x-axis on a restricted interval just from 0 to 6. And we've got the acceleration function, a of t, which is the cosine of pi t over 2. And we want to find the particle's velocity at t equals 3 if the velocity is 1 when t is 2. So it's just a differential equation here. To find the velocity function, we're just going to integrate the acceleration function. And so to integrate the cosine of pi over 2 times t, we're going to let u equal pi over 2 times t, so that du is just pi over 2 dt. So when we put this into our integral here, it's going to look like we're going to have an integral of pi over 2 cosine pi over 2t dt. And if we put a pi over 2 on the inside, we have to put a 2 over pi on the outside, right? And so then now we can turn this into 2 over pi times the integral of cosine u du, which is just 2 over pi. And then the integral of cosine is sine, so it's 2 over pi sine of u plus our constant. Well, it's really 2 over pi times the sine of, like we said, u, which is pi over 2t plus our constant. So we can then say, well, if the velocity is 1 when t is 2, we can say that 1 equals 2 over pi sine of pi over 2 times 2, right? Because we're going to plug in this 2 here for t. Pi over 2 times 2 is just pi. And the sine of pi is 0, so we just end up with a constant of 1. Looks like we're kind of running out of room in the space there, but we'll just kind of slide over here. That means our function v of t is the function 2 over pi sine pi over 2t plus 1. And if we want v of 3, that should be 2 over pi sine of 3 pi over 2 plus 1. And the sine of 3 pi over 2 we know is negative 1. So this becomes negative 2 over pi plus 1. So that's our velocity at t equals 3. Okay. And then for the second part here, we want the position at t equals 5 if it starts at the origin. Well, in order to find the position, we need to get a position function. We'll call it x of t. And I'm going to use a different color here. So x of t is going to be our integral of v of t, right? V of t is our function for v of t that we just found was 2 over pi sine pi over 2t plus 1 dt. And so in order to integrate that, we kind of need to do the same sort of u substitution there. But this time, I think we understand that, like, if the u substitution is going to be for the pi over 2 times t, then we're going to have to put a pi over 2 inside and another 2 over pi on the outside in order to integrate this. So really what ends up happening is we end up with, I guess we can write it out. So when we write it out, it's going to become, we'll have the 2 over pi that's on the outside. We can bring this to the outside. And then if u is going to be pi over 2, then we're going to need to put another 2 over pi out here to cancel out with the pi over 2 that we're putting on the inside to go with the sine of the pi over 2t plus 1, multiplying that by pi over 2, and then dt. And of course, when we integrate this now, right, this just becomes the sine of u plus 1 inside of here. So we've now got 4 over pi, and then the integral of sine of u plus 1 du, the integral of, sorry, not 4 over pi, but 4 over pi squared, And the integral of sine of u is negative cosine, right? So what we end up with is negative 4 over pi squared cosine u, or cosine pi over 2t, plus the integral of 1, which is just t, plus some other constant, which we'll call d. We can find d really easily here. The particle starts at the origin. So if our particle starts at the origin, that means that when t is 0, then the position is equal to 0. So we're going to say 0 is equal to negative 4 over pi squared cosine of pi over 2 times 0 is just 0, plus 0 plus d. Well, since the cosine of 0 is 1, we just end up with d is equal to 4 over pi squared when we add that over to the other side. And so now we can, we're going to need a new page now for this, but we can write out our position function. Right? So our position function now, x of t, is going to be our negative 4 over pi squared cosine of pi over 2t. And then we'll have a plus t and plus our d, which was 4 over pi squared. And if we want to evaluate that at 5, right, that's what we were asked for, x of 5, that'll be negative 4 over pi squared cosine of 5 pi over 2 plus 5 plus 4 over pi squared. Well, the cosine of 5 pi over 2 is just 0. So this whole first term cancels out, and we just have 5 plus 4 over pi squared. And that's our final answer for part B there. For part C, we've got another particle moving along the x-axis with a new velocity equation. We want to know during what time periods, if any, do the particles have the same sign? Well, first of all, the velocity function for this new one was 2t minus 3, so its acceleration function, we're going to call it a sub n for maybe the new function. Maybe we'll call this, probably should have called that v sub n, is just equal to 2. So its acceleration is always positive, right? 2 is always positive, right? So this is always a positive acceleration. And then for our other a of t, our cosine of pi t over 2, we just need to see when is that equal to 0 on the interval from 0 to 6. Well, it's equal to 0 whenever the angle is either equal to pi over 2 or 3 pi over 2. Right? Those are when our cosine function equals 0. And really, that's like the angle is equal to pi over 2 plus any pi n, because 3 pi over n works, and 5 pi over 2, and 7 pi over 2, and so on. They all work. So what we'll do is we'll just multiply by 2, giving us pi t equals pi plus 2 pi n. And then we'll divide by pi to give us t is equal to 1 plus 2n. And so anytime that t is equal to 1 plus 2n, that's when this thing changes its velocity potentially. So if n is 0, that'd be 1. And if n is 1, then that'd be 3. And if n is 2, then that'd be 5. But if n is 3, then we're at 7, which is outside of our interval. So the sign chart we need to make just needs to include 0 and 6 as our endpoints, and then 1, 3, and 5 in the middle to see what the sign of this function is. I'm sorry, the sign of the function, like whether it's positive or negative, is on each of these intervals. So if I put in something, let's say like 2 into my acceleration function, I end up with the cosine of 2 pi. Right, if we put in something like that, we get the cosine. Sorry, not of 2 pi. If we put in 2, we get the cosine of pi. And the cosine of pi is negative 1, so we know that on this interval it's negative. If we were to put in something like, let's say, 1/2, then we'd end up with the cosine of pi over 4, which we know is positive. If we put in something like 4, we'd get the cosine of 2 pi, which we know is positive. And if we put in something like, 5.5, or we could say 11 halves, we'd get 11 pi over 4 inside of there. And the cosine of 11 pi over 4, well, 11 pi over 4 is in the second quadrant, and that's where cosine is negative. So we can see that they have the same sign, right, when they're both positive. Right? So that'd be from t equals 0 to t equals 1, and also from t equals 3 to t equals 5. And then we want to know what time periods do they have velocity having the same sign. Well, our velocity function up there, 2t minus 3, that just equals 0 when t is 3 halves. So if we make a sign chart there between 0 and 6 with 3 halves on it, we can see that something like 1 makes this negative, and something more than 3 halves but less than 6 makes it positive. So that's the sign of the velocity of the second particle. Then the first particle, we had the velocity function for the first particle. We found that back in part A, right? And that was the velocity was equal to 2 over pi times the sine of pi over 2 t plus 1. And so if we have that, we should be able to tell that, like, if I take the sine of anything, right, I get a value between -1 and 1. And if I take that value that's between -1 and 1, and I multiply it by 2 over pi, 2 over pi is, we'll just approximate, like, it's around 2/3. So really now, the smallest I can be at is, -2 over pi, which is between -1 and 0. And if I add 1 to it, I'm always going to get a positive. So this thing is always greater than 0. Therefore, they have the same sign from t equals 3 halves to t equals 6. And that's the only interval, because the velocity of the other one is never going to end up being negative. So that's it for question number 2. For our next one here, we just want to find the position of this particle. We're given its velocity function, and we have an initial position of 3. So in order to find that, we'll just integrate the velocity function. 9t squared will become 3t cubed. 18t will become 9t squared. And minus 7 will just be minus 7t. And of course, we'll put our constant. When t is 0, our position should be 3. So we end up with 3 equals, well, if t is 0, that's 0 plus 0 minus 0 plus c. So our constant is just 3. And our position function was pretty straightforward here. It's just s of t is 3t cubed plus 9t squared minus 7t plus 3. For the second part here, we want to know when is the particle changing directions. So that can be when its velocity is equal to 0. So we just set 9t squared plus 18t minus 7 equal to 0. That looks like it actually factors fairly nicely with a 3t and a 3t here. And then one of them is going to get a minus 1, and the other is going to get a plus 7. Right, you check that out. That's a 21t and a minus 3t gives you an 18t. So that factors out really nicely. Setting that equal to 0 tells us that t was either going to be 1/3 or -7/3. -7/3, though, we'll ignore because t has to be greater than or equal to 0. So our particle potentially changes directions at 1/3. And we can see if that's true by just testing a value in our velocity function that's between 0 and 1/3, and then something more than 1/3. So if I put in something more than 1/3, like a billion, right, these are both going to be positive values here, and we're going to have a positive velocity. But if I put in something like 1/6, well, if I put in 1/6, 3t plus 7 is still positive, but 3 times 1/6 is 1/2, and 1/2 minus 1 is negative. So when I multiply the negative times the positive, I get a negative. So the only place that this particle changes directions is at t equals 1/3. It goes from going left when the velocity is negative to right when the velocity is positive. And for this last one here, we want the total distance that is traveled from t equals 2 to t equals 5. So since we knew that the velocity was always positive here, we don't actually have to do the absolute value of this function. We can just integrate our velocity function from 2 to 5. Right? So I'm just going to integrate from 2 to 5 the velocity function, 9t squared plus 18t minus 7 dt. Right? Normally, right, absolute value of velocity is speed, and its integral gives us the total distance traveled. But since v of t is greater than 0 on the interval from 2 to 5, then it doesn't matter, right? Then the absolute value of v of t is just equal to v of t. So I can just integrate v of t from 2 to 5. There's no change in direction. We already did that integral. It's 3t cubed plus 9t squared minus 7t. And we'll evaluate from 2 to 5. So if we plug in 5 to 3t cubed, that'll be 125 times 3, which is 375. And then 5 squared is 25 times 9 is 225. Minus 7 times 5, which is 35. And we'll plug in 2. 2 cubed is 8 times 3 is 24. 2 squared is 4 times 9 is 36. And minus 7 times 2 will be minus 14. So we got 375 plus 225. Well, that's 600 minus the 35 is 565. And so we got 565 minus 24 plus 36 is going to be 60. And then 60 minus 14 is going to be 46. So we got 565 minus 46, which is 519. So it traveled 519 units in those 3 units of time. I don't know if they were seconds. And that's the end of this assignment and this problem, and the end of the walkthrough for more integral motion homework.